Okay, so thank you very much for coming, everyone. So I'm Tim Lucas. I'm leading this. I'm going to be talking about disaggregation regression, kind of what it is and how to use it, and focusing on this R package. Well, Anita Nandi wrote, but I supervised. Rohan's here. Rohan has also contributed a lot to various parts of this work. We'll see some of his figures from his paper later. So hopefully he'll help answer any questions that I do badly on. We're going to be talking about disaggregation regression. So the structure of this whole workshop, I'm going to do a really quick introduction, 2 slides just to say, very quick overview of what it is. A really quick practical. I sometimes feel like going through a very simple example of the code without going into any of the details or any of the extra options can sometimes just give like a skeleton to sort of know what you're working with and, give something, I mean, not physical, it's on a computer, but something kind of a bit more tangible to kind of help make things feel a bit less abstract. Then I'll talk a bit about what disaggregation regression is for, what's the sort of motivation for these methods, then how it works, what it's actually doing, the mathematical model behind it. Then a bit of a description of what's in the disaggregation regression package, the disaggregation package. So it's not everything, it's got something. So I'll give an overview of that. And then we'll go through a detailed, longer practical where I'll give you much more information on some of the options available, what the code's doing, why it's doing it, and some of the practical considerations you might want to think about if you're running analyses like these for yourself. And at the end, there's some references or further reading if you're interested. So really quick introduction. So disaggregation regression, the general idea is if we have our response data, which might often be disease counts, but can be other things, if that has been aggregated to areas like the data on the left here, but we have perhaps our covariate data or some of our random effects we want to be at kind of a high resolution, like these covariates in the middle. How do we combine those data to answer questions that we're interested in? So one thing we might be interested in is getting getting high resolution predictions, but using this low resolution response data as our kind of main source of information. So yeah, we're looking at, we've got areal data, but we also have these kind of higher resolution covariates. Possibly we want high resolution raster level predictions, or we want to understand the processes that are occurring at these kind of small local like areas. And so very broadly, the way we do that is we just model this aggregation process explicitly in the model. We'll see that in some equations later. And so another way of saying that is that if we're talking about disease counts, we're just in the model, we're saying that the number of disease counts in an area equals the sum of all the disease counts in each pixel in that area. You just add them all up. I'd probably switch sort of a bit, I go back and forth between saying like areal and polygon and low resolution data for this kind of area data, and saying raster and high resolution data for the high resolution data. So those two things are just the two multiple words for the same thing on those two sides. So just say again, I might call this polygon or areal or low resolution, and I might call this raster or high resolution, and I'm pretty inconsistent about it. Sorry about that. So really quick introduction to how this works in terms of using the disaggregation regression, the disaggregation package in R. One thing to say, if you copy this code from the PDF, you'll get these quotation marks aren't normal quotation marks, so it'll go wrong. You'll have to replace them. But if you use the script that I gave you, it should all work fine. So broadly, what we'll be doing is we'll be reading in a bunch of data. One of the difficult things about these analyses is that we've got all these different types of data in different sort of formats and shapes. So we've typically got some shape files, which define the kind of geography we're talking about for the aerial data. Some population data on a high resolution raster, which isn't necessary, but often makes sense or sort of helps make things better. Some covariates in a like, it's called a raster stack. So it's a bunch of rasters all on top of each other, stacked together. So we read in a bunch of rasters. And then this prepared data function from the disaggregation package is doing quite a lot of heavy lifting. It extracts all these, all the raster data sort of. So for in this area, it gets every sort of pixel value in there, and gets it all in a format that's useful for analysis. And then we go on to fitting the model. So we use one function to fit the model, and we use a separate function to predict the model. So nothing here is very unusual, I don't think, but that's the simplest version of the full model fitting process. So hopefully when we go back and go through this in detail, you'll at least have sort of been exposed to it once, and hopefully you'll remember kind of what I was talking about a bit. There's a message. I think the sort of mathematical methods, Joseph, are totally applicable for disaggregating from coarse polygons to sort of medium resolution polygons. The package we've written currently is only written for going from coarse polygons to rasters. Depending on what data you've got, what you can do is to fit a model with coarse area response data, high resolution raster covariates. Then when you've got predictions at this kind of low resolution, you can aggregate those back up, which is just quite a simple like geographic operation in R. And so if you want predictions at the area level, you can aggregate back up and use those predictions. All right. Okay, so to kind of start from the beginning again, the kind of the situation you might be in where you might want these methods is if you've got your response data aggregated at area level, or are fundamentally at area level, not necessarily aggregated, but exist at an area level. But your covariates are at a higher resolution, often rasters or some other high resolution. You might want raster level predictions for various policy reasons. If you want kind of really directed policy recommendations, for example, or if you want to use those high resolution predictions as a substrate for other kind of ways of thinking about optimizing delivery of a vaccine or something, we might want these raster level predictions. Or you just might be asking kind of fundamental scientific questions, but you're interested at what's going on at this high resolution level rather than interested at what's actually happening at the aggregated level. So for example, so the kind of the questions you're asking when you're sort of using these different levels is are subtly different. So if you're asking questions at an area level, you might be asking something like, how does the average rainfall across this county affect the average malaria across this county? Whereas at the raster level, you're kind of asking, how does rain in this very small area affect malaria in this very small area? And there's some cases where that really might change what you're thinking about. So for example, if you've got a spatial random effect that's smoothly varying across space as part of your model, you might think that pixels just across a border from two areas might actually be more similar than two pixels within an area but on opposite sides of the area. And so in some cases, these kind of areas are quite sort of artificial and arbitrary, and a lot of the processes are really kind of occurring on kind of a much more continuous scale. But we've sort of, for various logistic reasons, we've sort of placed these sort of political boundaries on things, for example. So a naive solution to this problem is to fit a model at area level and then just use the coefficients from that fit multiply kind of coefficients to covariates, but using high resolution covariates. So fit a model at area level, but then just make predictions at the raster level without kind of doing anything, just use the coefficients you've estimated. And this assumes the processes that are occurring are similar at the area and raster level. And this runs into what's called the ecological fallacy. So again, we've got these two questions that are subtly different. How does the average how does the average rainfall across the county affect malaria versus how does the rain in this small area affect malaria? And so the answers to those two questions, while they're subtly different, the questions are subtly different, but the answers can be really quite different. So if you're thinking in terms of coefficients, the sign of those coefficients can totally switch going from one spatial scale to another. So like conceptually, you can get the opposite answer to your question just by changing the spatial scale. So to try and sort of explain this ecological fallacy a bit more, I've got this kind of example that's hopefully intuitive enough that people can sort of make sense of it. So if we're looking at the relationship between wage and health, and if we've got data at area level, so some areas the size of kind of whole cities and perhaps, you know, areas in the rural areas sort of city size or slightly larger. So at this area level, cities have a high mean wage and poor health, I think is a fairly true across most of the world, whereas rural areas may have kind of a medium mean wage and pretty high health. So if we fit a model to this aerial data, we'll find the relationship that high wage predicts poor health. And if you fit that model, but then do this naive process of simply predicting on the high resolution data, so if you predict within cities, this model will say that the poor inner city areas have very good health, which is totally wrong. You can see that this modeling process has not done what you wanted it to do at all. And so there's two things that drive this. I've got one written, and Ryan mentioned one last week. One is that the heterogeneity within cities drives this mistake. So high is the high mean wages in cities is driven by a small percentage of very rich people, and then that coupled with non-linear. This is actually hard to explain without having gone through the maths, but for example, if we're talking about disease in terms of disease counts, what we might have is wages. You might sort of relate the exponential of the wage to the disease counts, and so you're going through this non-linear function, and so therefore the wages, the mean wage is the exponential of the mean wage is very different to the mean of the exponential wage. So that's kind of how that arises quite explicitly there, and hopefully that'll be a bit clearer when I talk about show some equations in a minute. There's not going to be many equations, and they're not complicated, but they're there just to kind of communicate. So the solution is, or one solution is disaggregation regression. So in disaggregation regression, we explicitly model this aggregation process. So we're sort of, the model is fully defined at the high resolution, but then in order to link these two scales, we have the full model defined at the high resolution and then have an aggregation step that we can then use to link to the low resolution. And because of this, it avoids the ecological fallacy. So I'm going to try and explain this in a way that's hopefully a balance between being very explicit so that you truly understand what's going on, but also without getting stuck in details. So we'll start with just like a normal Poisson regression, and then we'll see what has to change in order for it to become disaggregation regression. So here we have a typical Poisson regression. We have probably the predictions of our response variable, yi. So for each for each sort of data point, we've got YI disease counts in this example. We've got two covariates, X1 and X2. And so for each row of data in the response variable, we've got one row of data in the covariate data. And we've got three regression parameters, so two coefficients that relate the covariates to the response and an intercept here. And then the link function here is an so it's a log link function, but we put it on the other side of the equation, so it's an exponential sort of inverse link here. And so this is what a typical Poisson regression looks like, and the way kind of we do inference, I don't know whether this is kind of the wrong scope, but we can think of this as a generative model. If we guess some values of the beta parameters, we know the x's, so we can, if we guess these beta parameters, we can put all the numbers in. We can we'll then get this estimate yi of cases, and then the way we tell whether that is whether those regression parameters are good or not is we compare these predicted yi's to our true observed yi's, which are our observed disease counts. And so we can we can make a first guess with these parameters. We can see whether they're a good guess, and then the process of kind of maximum likelihood is moving through parameter space until we find a set of these parameters that are the most likely, the maximum likelihood parameters. And similarly in Bayesian analysis, you're moving through this parameter space and just saying, for each of these parameters, are they good or bad? So that's how typical Poisson regression works, broadly speaking. And disaggregation regression, again, for now, we'll talk about it in terms of disease counts, and so kind of the direct analog to Poisson regression. It's quite similar. But we've got this aggregation step, this summation step here. So again, we've got for each area, we've got predicted disease counts, and we've also got our observed disease counts. But now for each row of response data, so each I, we've got a number of pixels. So the pixels in the rasters are indexed with a J. These two are the wrong way around. Sorry, this should be J in I. So for every pixel J in area I, we have a value of the first covariate, and we have a value for the second covariate. And so we can, again, think about this as a generative model. We can say, if we made a guess for our parameters, we then know all the covariate values ij. So for one area, we know all the, say, 100 pixels. So j for I to 100, or the 100 pixels. We can put those in, multiply, go through these exponentials so that we're only ever predicting positive counts. So in every pixel, there's somewhere between 0 and infinity disease cases. And then for each area, we add all those pixels together. And then again, we get our predicted yi, which in the same way as before, we can compare our prediction yi to our observed data yi, so our observed counts. And so again, because this is a generative model, again, we can do the same thing. We can sort of move around parameter space, trying to find the maximum likelihood values for these parameters, or we can move around parameter space, saying how the probability of each of these parameter sets, if we're in a Bayesian framework. And so, broadly speaking, this is all disaggregation regression is. Okay, so this is a generative model. We can, for any given parameters, we can, because we know all the covariates, we can just sort of push this forward through the model to get predictions of yi, and then we can compare them to our observed data. Now here's a picture, kind of the same thing. So our covariates and spatial random effects and various other things are down here in this kind of pixel resolution. Our response data is here at this kind of polygon resolution. So here we've got the whole of India is one area, so one data point for the whole of India. We would presumably have other countries as our other kind of response data points. And so we've got some covariates and some parameters. If we multiply those covariates by their learned parameters and push them through an exponential function, for example, we'll get an incidence rate. So that's the number of cases per person per year, for example. And if we multiply that by a population raster, we'd then get a pixel level cases. So the absolute number of cases per year in each pixel. And then we take all those pixel values and we add them up, and that gives us a polygon cases, and we can compare that in the likelihood to our observed polygon data. So that was kind of the more specific Poisson version of disaggregation regression, but it is a bit more general than that. So you don't have to use an exponential inverse link here. You can use whatever inverse link you like. We can add model components. So as well as some covariates, we might have some more covariates, and we might have a spatial Gaussian process. So I'll show you a bit what that looks like in a minute, but it's kind of a spatial random effect. This thing we often want to do is multiply the disease rate, that's this whole section, multiply that by the population. That should be a J, the population in pixel J. So we're going from kind of incidence rates to pixel incidence counts, and then adding all those up using this section here. And YI doesn't have to be a Poisson, it could be a normal distribution or a Bernoulli distribution or a binomial distribution or whatever sort of makes sense for your data. So this question, so this sort of this idea of what is disaggregation regression, we can talk about it as this very vague general term for models with an aggregation step. It was kind of, I think, the first sort of people that we've seen writing it down were Kiel et al. With applications in ecology. The first examples we've seen in disease was Storek et al. This paper was really the one that inspired us at the Malaria Atlas project, I think. But yeah, so based on that, the Malaria Atlas project, we thought that that's a good idea. I'm not at the Malaria Atlas project, but I was at the time. Driven by you and Cameron, as far as I remember. Yeah, we were inspired by this Storek paper et al. And we kind of developed the methods, worked out when they worked and when they didn't, various other kind of practicalities, and used them in large analyses, which I don't think had been done before. And so while disaggregation regression is this vague general term for any model with an aggregation step, the disaggregation package is more specific. So first to say it's written by Anita Nandi, some contributions by Rohan, and I was involved at all. I was involved as well, sorry. I'm in practice maintaining it, although officially I'm not. I think as soon as anyone wants us to change it, Anita will hand over the maintainership to me. So we've specifically built this package for spatial data to deal with some of these kind of data. One of the most difficult things about this is that you've got all these different types of data that are different shapes, different sort of object types in R. So we've kind of focused on that to try and make that step easier. It's a relatively restricted set of models. So it's linear covariates, a spatial random effect, that's a Gaussian process, and IID random effects. I'll go through all this in more detail in a bit. A relatively limited number of likelihoods at the moment, so Poisson, linear, and binomial. If anyone particularly wanted negative binomial, I'm sure we would implement that. But until someone asks us, I think we probably won't at the moment. It's only Bayesian inference at the moment. There's more details at the end of the talk, but I'll skip that for now. But basically, it's Bayesian inference only. We use this package TMB as a backend that makes it fast. Various computational tricks that make it feasible to run these models. They can be very slow, and it's on GitHub and CRAN, which is I guess most people have installed it from CRAN before here. Okay, so I'll go through some of that a little bit more slowly before we get to the kind of tutorial in a bit. So yeah, there's a few likelihoods implemented at the moment: normal, likelihood, Poisson distributions, and binomial. There's some open questions about what a binomial distribution actually means in this kind of disaggregation regression sense, but we haven't really thought about that. We've thought about it a bit, but not that carefully. So if you think about it, please let us know what you decide. If you want something else, adding likelihoods is quite easy, I think. So if you want something else, please just open a GitHub issue and we'll probably do that for you. Fixed effects, they're only at the raster level. So you could imagine it'd be useful to have some raster level fixed effects and some area level fixed effects. At the moment, there's only raster level, and if you want area level, you just sort of have to take the area level ones and like stamp them onto a raster as a way to like fake it. The priors on the fixed effects are only normal at the moment. That's a consequence of the particular way we do Bayesian inference in this package, so that's not going to change anytime soon, I don't think. So we have IID random effects in this implemented in this package. So it's one parameter per area, which is therefore very over parameterized. One parameter per data point plus all the other parameters in the model. It is over parameterized, but it can model useful things like over dispersion in a Poisson. So if your data are counts but don't look like a very beautiful Poisson distribution, you probably want to have some way of modeling this over dispersion. Negative binomial is one way of doing that, but we've typically been doing it with these IID random effects. We found them really vital for various reasons. If you don't have this IID random effect and you're using Poisson or binomial likelihoods, what we find is your spatial random effect gets messed around with and is forced to do really stupid stuff. So we found this really vital. Or you could use this to model missing covariates. So we'll talk about the spatial random effect in a minute, which is also probably modeling missing covariates. But if you have some missing covariates that if you think there is some things happening at the polygon level that you don't have data for, this might be a good way of modeling it. So for example, if you're modeling malaria as an example, and like different states distribute different numbers of nets, or different states kind of count their cases slightly differently, this might be an appropriate way to model that if you don't have the data on that. We found it vital. So yeah, this idea that it screws up the spatial random effect is kind of a similar idea to BIM models, if people have seen that. You have a spatial term and a IID non-spatial term, and that's partially to stop the model forcing variance into the spatial component. And it's also a way of, if part of your question, analytical question is how important is space, you kind of need to have a way for the model to model something without space or model with space, and then it's sort of a true reflection of how important space was, if that makes any sense. And so the hyper priors for these models at the moment are these penalized complexity priors. So the way the IID random effect works is each area gets a parameter, like its own intercept, and that parameter is either, you can think of it as either from a normal distribution with mean zero and a standard deviation, or you can think of it as having a prior of a normal distribution with mean zero and a standard deviation, but we want the data to tell us what this value for the standard deviation is. So this standard deviation is a hyperparameter for the IID random effect, and we put a hyper prior on it. So this penalized complexity prior is our hyper prior on the standard deviation. And the way we define these are, so some of the maths behind them is not totally simple, but the way they're sort of defined in our package and in other packages, I find quite intuitive. So we say we use our a priori knowledge to define a probability that the standard deviation, so this standard deviation that's controlling how flexible this IID effect is, define a probability that the standard deviation is greater than a number. So we typically use a probability of 0.01. So we're sort of saying a 1% chance that the standard deviation could be bigger than this. So we're kind of saying we're pretty sure it should be smaller than this. And then we choose this standard deviation number. I'm saying the probability that the standard deviation is greater than some number that we choose based on our understanding of the data. Often just looking at the scale of the data is 1%. So here we've got the probability that the standard deviation is greater than 1 is 1%. So, and then from there, the penalized complexity prior kind of smoothly prefers simple models. So if the data isn't quite strongly telling it to make this IID effect be important and flexible, it will the prior will push the IID effect to be sort of not flexible and therefore not important in the model. So as well as this IID random effect, we've also got this spatial random effect, and the way we model that in this package is a Gaussian process. So it's a smoothly varying but non-linear surface over space. So in this picture, if we imagine this is latitude and this is longitude, and then the y-axis here is I don't know if you call that y. Anyway, the vertical axis here is like how important is the effect of space at that point. So up here where the effect is high and you've got these red colors, it's saying that in that area there's a high number of disease counts, if we're talking about disease counts, whereas down in these blue areas it's saying that there's a low number of disease counts. And this non-linear surface is learned by the model as alongside the rest of the model. This whole surface is learned at the same time. So we use a return covariance function, which is, so we're saying how correlated is the spatial effect here versus based on how far away another point is, how similar is the spatial random effect there. The return covariance function is I can't remember exactly the rationale, but it's quite a sort of natural way to model these in space. Is a very sort of standard covariance function for these spatial Gaussian processes. And this spatial random effect is, here it's controlled by two hyperparameters, the length scale and the marginal standard deviation. So I'll talk about the details of them in a minute. There's this third parameter, smoothness, that's also a hyperparameter, but we don't try and learn that along with the rest of the model. We fix it. The three combined, you can't learn all three of those parameters all at once. So we just fix smoothness. Again, this is relatively standard in the kind of geostatistical community, I guess. But the two parameters we are learning, one is this length scale that we refer to as rho. So that's the distance before the correlation in the spatial random effect reduces to 0.1. So if you've got a point on the random spatial random effect here, how far away do you have to go before these 2 points are not particularly similar until they're kind of essentially uncorrelated? So 0.1 correlation is a fairly low correlation. It's kind of close to uncorrelated. And we've got this second hyperparameter, the marginal standard deviation. That's how big is the variation. So the first one saying how long does it take for the kind of the field to change. But then the second one is saying how kind of the magnitude of those changes. So there's kind of four kind of quadrants. If you've got length scale and the marginal standard deviation, the length scale is saying how wiggly the random field is. The marginal standard deviation is saying how big the kind of fluctuations in the random effect is. So if you've got a short length scale and a big marginal standard deviation, you have very big, very wiggly lines, like surfaces, sorry. If you've got a long length scale, but a large marginal standard deviation, it will change slowly over space, but it will change a lot. If you've got a long length scale and a small standard deviation, it will change slowly and not much. I don't know, I'm running out of ability to draw these pictures in the air. And I can't remember what the last one I said was. If you've got a short length scale and a large and a small standard deviation, it might wiggle very sort of quickly, but it won't change. It won't have big magnitude wiggles. I think wiggly is a accepted term in this kind of field now. Wiggly. And so again, we control these hyperparameters with hyperpriors, and again, they're penalized complexity priors. So we're defining the probability that the range is less than a number. So we're saying we don't think that this kind of spatial random effect should be so wiggly that it's varying a lot in less than 20 sort of spatial units, for example. So we're saying that's a 1% probability, and the same kind of probability that the marginal standard deviation is greater than the number is a probability. And same again, this hyperprior is penalizing the hyperparameters to prefer long-range, small variation random effects unless the data overrides this prior and tells us kind of quite confidently that the spatial random effect should be wigglier or biglier. Okay, that's the kind of the theoretical overview. I've missed it now. I normally ask, last time I asked people to go through the short tutorial on their computers, but I forgot. So if there's any questions at this point, I'll very happily take them. Otherwise, it's probably worth us having a 5-minute break just to grab a drink or something, and then after that we'll go into the sort of in-depth tutorial where we'll go through together line by line through the script and see how everything works kind of in practice. Okay, so we're going through this practical now. So if you have your R script open, and we'll go through it line by line. Some of the bits are a bit slow, so probably when there's the slow bits, I'll again ask you to put something in the chat so that I know when people are finished, so that I don't, constantly move on before people are ready. So if we open the script, the first sort of few lines are just the really short version. If you skip those and get to the bit where it's sort of, I can't remember exactly what it says, but it says slightly more in-depth script or something. It says longer version starting from line 42 or so. If you go from there, so obviously you need to set your working directory so that you're in the same working directory as the script is. And so the working directory below where all the data is, if that makes sense, given these file names. And the first step is to read in these shapefiles. So shapefiles is the word for these polygon definitions, this kind of spatial data object. I don't have time to really give a full introduction to all these spatial objects. I imagine a bunch of people on the call have been using them fairly routinely. I'm sure there's some people that haven't. So I think I'd best I'll give you an overview of what they look like, but I'm not going to go through all the details of them, and you can go back and look at that if you like. So we're going to read in the shapefiles. If you look at the class, you'll see there's a spatial polygons data frame. There what's called an S4 method in R. So it's a bit like a list, but instead of accessing what's called a slot, instead of using a dollar, use an at. So if you look at this shapes at data part of the object, that's a data frame, and that's where all the kind of associated data is. So you've got the kind of geographic definitions of where these areas are, and you've got data that represents one row per area, various sort of measurements or whatever for that area. So if we look at the shapes at data $ints column, so this is a column of the data frame. If you look at it, it's some numbers. If you do a histogram, it's some numbers. So these are the disease counts from, so this is malaria data. It's the number of malaria counts in each area. If you look at this, if you look at the data directly, they're not integers, and that's because we did some pre-processing steps to account for some biases in like treatment seeking and things, but we're going to treat them as counts, and this all works fine. And so you get something like this. If you do plot on the shape object, you get a plot of just the shapes. So it just shows you sort of geographically what they look like. This for me, for some reason, is going really slow, but if you do sp plot shapes and then tell it which column you want to plot, it gives you this this plot. So this is the malaria counts in each area. So so yeah, down on this. So these aren't like normalized by population at all, but down along the coast we have a lot of malaria cases, and kind of this area and this area we have a lot of malaria cases. I could have shown you in the covariates, but I didn't. But this area in the middle is like the highlands, so it's a bit cooler and there's less malaria. This is counts per area, not rate, if that makes sense. So it's not per person, it's total counts per area. I hope that makes sense, Pablo. And so we'll be incorporating the population at the high resolution raster level. We'll see that in a minute, I think. So yeah, we've got this malaria case data. And then we want some population data. We want this population to be at the raster level, because we want, if a very small area has virtually nobody living in it, that we sort of already know a priori that area can't contribute thousands and thousands of cases to the total. So in a way, we're just weighting the pixels by population. Say, like, if a pixel has got lots of people in, then even sort of medium malaria in this case can cause quite a lot of cases total. So we're reading this population in as a raster again. So this raster data is just like kind of a matrix or a grid of numbers, but for kind of computational reasons, it's kind of called a raster and treated slightly differently, and it's stored as these TIFF files. If you look at the class of that object, it's a raster object, a raster layer, I think it's called. If you just plot the object, you'll get this plot. So I think the capital city is here in the Highlands somewhere. If you plot it log 10, you'll see a bit more sort of actually what things are looking like. So yeah, so we've got the shape files and the raster data now. The raster population data. And then we read in some covariates as well. So in this raster, in this disaggregation package, we've provided this get covariate rasters function, which is kind of a shortcut to get a bunch of rasters all in the same shape, in the same extent, the same resolution. So you give it a directory name, and it reads any rasters that are in that directory, does a bit of pre-processing to get them all to match up. You give it like another raster to match to. So whatever, it takes all these covariate rasters and makes them look kind of like this. You might want to, instead of using this function, you might want to do all this manually. There's like, you can spend your whole life caring an awful lot about how to do all this geographic data pre-processing stuff. So one way we imagine you might do this is do a bunch of pre-processing manually and then store those pre-processed rasters in a folder, and then use this just to kind of quickly get them. Not sure what the best use is. So the class of this object you've just read in is a covariate stack. So that's a bunch of covariate layers all combined into one object. And if you plot it, you get this plot that shows the covariates. So you can see they're already standardized. So they're already, minus the mean divided by the standard deviation, so that they're broadly got a mean of 0 and a, kind of standard deviation of 1-ish. I said that the center bit is the Central Highlands. You can see that here. This is a measurement of how green it is, the vegetation index. So you can see that this side is very green. I think that's because the wind comes in this way, hits the mountains and falls on that side of the island, so it gets very green there. And then the temperature and the standard deviation of the temperature. I think the standard deviation across the year or something. Anyway, so these are all things that are relevant to malaria. Okay, so we've read in the 3 sources of data. Our actual response data was already in the spatial polygons data frame. In practice, you might have that separately, and you'd have to do an extra step to join those 2 data sets. I guess I should say that a bit more carefully. So this shapes at data is just a data frame. So if you've got a separate data source and you want to add, say, your response data into that data frame, you can just treat this like any data frame and do a column bind or a left join or whatever is appropriate here. You just have to remember that this is ordered in some way, so it knows that the first row is the first shape. So you have to make sure that your separate data gets put into that same order. So this prepare data is quite a slow function. If you get this running and let it chug away for a bit, because it's doing quite a lot of geographic processing, we give it the shapefiles, including our response data. We give it the stack of covariate data. We give it the population raster. We tell it the name. So inside that shapes at data frame, there's a column called ID2, and that's the sort of the identifier for each area. So I can't exactly remember how this is used. I think if you don't put this here, it just makes an ID column for you. If you've got names of areas, it might be easier to interpret the output later if you tell it to use those. You need to tell the function what the response variable is. I'll go into this in a minute. That's a bit complicated. This is quite slow geographic processing, so we've written it so it's multi-core. So if you tell it to use 8 cores, it will use 8 cores, which will speed it up quite substantially, I believe. Here we've got whether you want this function to handle missing data. By default, this is false. But there's the way it handles missing data is a little bit crude. It doesn't do a very good job of this. So if you want to put NA.action equals true just to get your first model run, then that's probably quite reasonable. But you probably want to go back, if you do have missing data, you probably want to go back and think about how to handle all your missing data carefully. So it does different things for different types of data. So if your response data is missing, it just removes that data and ignores it. If your covariate data is missing, I can't remember exactly what it does, but I think it imputes it as the mean of the covariates in the area that it is from, or something like that, which is not very sort of principled. That's definitely a bit of a nasty hack. And if your population data is missing, it assumes that it was 0 population, which is not a terrible idea, I guess. So it is saying if you don't have any population data, there probably isn't anyone here, or maybe it's kind of accidentally the area has gone over into the sea a bit or something like that. And so it just treats that as 0 population, which then means that pixel can't contribute cases or can't contribute to the rest of the model. So I hope people got this running. I'll explain this mesh stuff, and then after I've explained the mesh stuff, I'll check if everyone's that bit of the model, that bit of the code has run for everyone, because it is a bit slow. So the spatial random effect that's in these models, this smoothly varying Gaussian process. One of the computational tricks that's used in this package is called the SPDE approach. It's used in the INLA package, if anyone knows that. And it sort of computes the Gaussian process on this mesh, which makes these models go from utterly impossible to fit because they'd be horrendously slow to acceptably fast. And so what we have to do is define this mesh, and kind of what we're doing is we want inside, in the areas where we have data, so Madagascar here kind of is a bit inside this black line, we want fairly small, fairly equilateral triangles over all the places that we have data. And then we want to extend the mesh a decent way past that point, but it doesn't matter so much how big the triangles are as we go outside the data. We're just protecting it against weird edge effects. So what these parameters do is we've got this parameter called offset, which is defining a distance between where our actual data is and this black line. So we're saying this black line should be drawn like one spatial unit outside your spatial data. And then this 2 is saying, and then also draw a line 2 spatial units outside that black line. So we've got this kind of inside and outside thing happening. We're saying the maximum length that an edge of a triangle can be within the black line is 0.7. So in here. And the maximum length that the edge of a triangle can be outside this black line is 8. So we get much bigger triangles out here than we do here. And then this is kind of a carryover from if you're using this approach for slightly different types of data. But what this mesh building algorithm does by default is it puts a node, so each of these black dots is a node of the mesh. It puts a node on everywhere that you have data. But because we've got this raster data, we have data absolutely everywhere at very high resolution. And so this cut is saying if we have 2 data points that are within 0.05 spatial units of each other, they don't each need a node. You can just put one node in the middle and that will be fine. So these combined sort of define this mesh. And so if you're using your own data, you kind of just have to play around with this. Slightly unfortunately, this is all done in this function that's quite slow because it's doing some other geographic processing at the same time. But you can kind of look at a map of your data, get a good first guess for some of these values and go from there. There's also good tutorials. If you search like INLA SPDE, you'll find good tutorials on more about what these mean and how they should be set. So that can be useful as well. It's called INLA. So in the instructions for the packages to install in the original email, I told you to install that package called INLA. It's that same package. Okay, so then after we've done that sort of data pre-processing step, we're then going to fit a model. The simplest version of this function, we give it this big data object that we just made, this data for model. We tell it what likelihood family we want, and we tell it what link function we want. So sort of standard log and Poisson if we've got counts. We might want identity and normal if we've got not count data. If you want a bit more detail, you can, in this function, you can say whether you would like this IID random effect or not, so true or false. You can say if you want the random field to be fitted, true or false. So if your model is very slow or you just want something to sort of look at to start with, you might want to set this to false. It will make things run a lot quicker. And you can define all your priors here as well. So it's on my to-do list. The documentation doesn't really explain how to do the there's a question. So there is some defaults for the mesh arguments. So it just guesses. So it does still make a mesh. It does still do the spatial random effect, but the mesh it makes by default in that case is really bad. What are the default parameters? I can't remember. You'll probably say it in the documentation. They're not good defaults though. Yeah, don't rely on those defaults. The defaults for the priors are, I mean, you shouldn't rely on defaults for priors either, but the defaults for the priors are not terrible. We've done some relatively sensible things so that if you just run a model, you'll at least get a sense of what's going on, hopefully most of the time. So I think in the script, at the very bottom, I've copied this whole big list of the names for the priors, and you can use those in this list to define any priors you like, but it's on my to-do list to add it back to the documentation. But here we've got the standard deviation of the normal distribution priors for the slope parameters, or the sort of regression coefficients. So here we're setting it as 2 instead of the default, I think, is 1. I can't remember. And here we got, so these penalized complexity priors, you say the rho is the length scale, you give it a minimum value of rho and a probability that the length scale is less than that value. So here we're saying that the prior minimum value that we think the length scale is 0.5. So we're saying 99% sure a priori that the length scale is bigger than 0.5. So yeah, then hopefully if you're fitting this is also quite a slow process because this is fitting quite a big Bayesian model. It's kind of this funny thing that we've only got like 150 sort of true data points, but we've actually got something like 100,000 pixels going into this model. So while it kind of, from a statistical point of view, it's quite small data, from a computational point of view, it's kind of quite big data. So kind of the worst of both worlds, but what are you going to do? So I will talk through the plots of this and then ask if people are finished. If you do a summary of the fitted model, you get some text giving you some posterior means and posterior standard deviations of your parameters and things. You can plot it. So this gives a plot of the parameters. So this is the 95% credible interval of each of the parameters. So we've got the slope 1, 2, 3, 4 are the 4 like covariate coefficients, the fixed effects. The intercept here is the intercept. Log rho is this rho, but on a log scale. Log sigma is the marginal standard deviation, again on a log scale. So if you want to turn it into sort of natural scale, you exponentiate these. And then we've got the hyperparameter for the IID effect as well. It also plots this in-sample performance. So it's just a plot of the estimated or predicted value for each area and the observed. You can see here that we get this almost perfect line because this is because the IID effect is kind of, it ends up being quite flexible, and the IID effect ends up making all the predictions close to perfect. So I think probably we should change this plot so that it ignores the IID effect for the plot, but we haven't done that yet. But that's what that's doing. So clearly there's a bit of overfitting, but it's not overfitting in the sense of your relationships between covariates aren't super overfit because you don't use any of the IID effects for your sort of outer sample predictions. Okay, so predictions from these models, I can't remember exactly. So the default, if you just predict the fitted model, it will make predictions over the entire raster covariates that you put into the model in the first place. I can't remember how you predict new areas. It'll tell you I think it tells you in the documentation. Oh, someone else had this problem as well. Was this? Yeah, I need to. It's an S3 method, so it should just work. But okay, thank you, Clyde. I'll look into that as well. I don't know why that's happening. But actually, I forgot that there's this predict_model function. That means you don't need to use the S3 method. That's useful. Okay, so we predict over the covariates that were put into our big data object in the first place. If we plot it, we get this plot. So this is the posterior predicted mean of, I think this is rate now. Yeah, so this is now the rate scale, in this case from the area. We've also got the lower 95% credible interval and the upper 95% credible interval plotted. But in this model prediction object, you've also got the different components of the model predicted as well. So if you want to look at what the field is doing, what the spatial random effect is doing, you can get this object out and plot that, and that's just a raster as well. If you want to mask it by the population raster so that it kind of looks like Madagascar, you can do that. So that gives you this. And so this looks like a fairly reasonable model fit. Like if this spatial random effect was wildly varying or not varying in a smooth way, then we would not be happy with this. If this was totally flat, we'd be a bit confused about why this had happened. And another thing you can see here sometimes is if the triangles in your mesh are too big, you'll see kind of triangular artifacts in here. And so that can be a useful check as well, to check that your mesh is a decent size. Yeah, I guess it must be a name. It is a namespace issue, but I don't know why. It seems to work for some people and not others, which doesn't make a whole lot of sense. The one person that had that last week, they restarted art and then didn't load the disaggregation package. So you could try doing library disaggregation just in case, but it sounds like that's not the case here. And I need to check some of this stuff. I haven't looked at it for a while. Okay, so yeah, you can plot the field. I think you can plot the IID effect as well, and you can predict, and you can plot just the effects from all the covariates as well, which is also useful. And so that's the more detailed practical done, actually. So in a minute, I'll go through some of the finer details in kind of some of the practical considerations when using these models, and some of the technical details that for most people won't be very interesting, but for the few people that are interested, it's worth just saying it. But it's definitely worth plans to update whatever that's called, simple features or something, spatial features, I can't remember. Yes, but I'm not. I mean, I'm aware that that's probably what we should do. I probably won't find time to do it myself anytime soon. So unless I can hire some postdocs who fancy doing it, I'm not sure that it'll happen very soon. If anyone's interested in that sort of stuff and wants to contribute to the package, absolutely, please do. I think we might want to make it use both for a bit at least. But yeah, I've seen some of the, just quite a number of other packages are kind of depreciating the sort of SP stuff now, aren't they? So it's really getting a bit old. I don't know what the stars package is, so I'll have a look at that at some point and see. But yeah, like I said, I don't manage to find a lot of time to maintain this at the moment. So, and no one else is doing it. So it doesn't, things don't get done very quickly. No. Okay. So while we're developing these methods, we kind of, we became quite aware that our intuition for things like statistical power didn't necessarily map from kind of normal models to these models. So in a normal model, you have one response data point and one covariate value for each covariate. But with this, because we've got multiple covariate values for each covariate, for each response variable, it's not obvious that kind of our intuition on statistical power is any good. So, you know, some of these sort of rules of thumb, like 30 data points is reasonable to estimate one parameter, something like that. We were very unsure how bad that kind of rule of thumb would be. So Rohan, who I'm not sure if he's still on the call or not. Oh, yes. So Rohan did this whole big simulation study, kind of trying to get an idea of kind of when these models work, when they don't, and things like that. So I'm going to build this plot up over a few slides, but we'll start with this one. So on the x-axis, we've got the number of polygons that are being used to fit models. Each dot is one simulation, so a simulated model we simulated the covariates and the response data, and then fitted a model to just the we simulated, covariates, response data, and some held out response data. And then we fitted the model to some covariates and some response data and tried to predict the within area pixels, I think. And so this correlation is how good our predictions are at something that we didn't have direct data on. It's something like 4 covariates and using the random field, the random whatever it's called, the spatial random effect. And so first thing to say, kind of as you'd expect, as you have more data, this correlation improves. So more data is giving us better fits. And so all the data points here are very large areas. I think they're states in India. And so up here we've kind of got 35 states worth of data, but therefore within each polygon, within each area, there's I think thousands of pixels. And just to note, we're starting with very small amounts of data here, 8 polygons of data or 20 polygons of data, which is absurdly small. But then as we move across this row, we're using smaller and smaller polygons. So I don't know if people have seen these terms before, but admin 1 typically refers to something like states, like US states or Indian states or Chinese provinces. Admin 2 is one kind of administrative area below that, so maybe municipalities sometimes, or I can't remember the other words. And admin 3 are kind of very small areas. So admin 3, there might be 1,000 areas in a large city, for example. They might be called communes or things like that, depending on the country. So as we move from here across, we see we get better predictions. So it kind of makes sense that if your polygons are small, you'd have not many pixels within a polygon, and therefore you don't have very heterogeneous environments within the polygon. And so therefore that polygon is more informative about the relationships between covariates and response data. So as we get smaller polygons, we get better fits, but also kind of here we've got, because there's only 30 states in the whole of India, but there's easily 300 of these admin 3. We also kind of can get more data total as we move across here. And then the 3 rows here are how misspecified the model is. So this top row, we simulated for a model and then fitted that exact same model to the data. And what we can see is you get very good fits nearly all the time, even with very small amounts of data, even with very large polygons. So for example, here we've got something like 15 states worth of data, these massive polygons. 15 data points is really not many data points at all, and yet we get good correlation between the observed, the sort of simulated raster level incidences and our estimated raster level incidences. And then it just improves from there. But then here we've got a couple of covariates that were not used in the simulation, but were in our model fitting process. And so things are a bit worse. And then here we've got even more covariates that are in one simulation and not in the model fitting process, or vice versa. And things get worse again. So if your model is very close to reality, which in these applications it very rarely is, you can really get really good fits relatively easily. But things get worse when you have more model misspecification. Nothing surprising, but in the presence of model misspecification, smaller polygons are better and more data points are better, kind of what you'd expect. So yeah, but we still have, so this is the sort of thing you can start using to build intuition about, have you got enough data, or are your polygons too big to be learning something useful? So I think this paper in general is very useful if people want to read that. It's linked, the full reference is in the last couple of slides. And then just a couple of computational details. So the package is running on this TMB backend. So the way that package works, you don't need to use this if you're just using the package, but you define the likelihood function in C++, which therefore means it's fast. It does auto differentiation for you, which means you can optimize parameter estimates quickly by using the gradient, which makes it fast. The spatial random effect is using this SPDE approximation, which is what the whole mesh thing's about. So it's an approximation to the Gaussian process, but it's quite a good one. And again, it takes things from being, especially for Gaussian processes, they scale with the number of data points. And here that would be the 100,000 pixels. So a full Gaussian process would just be untenable with these models at all. With this SPDE, they're quite acceptably quick. And this is the same thing that's used in INLA if people use INLA. In this package, we're not doing full Bayesian inference. Really, what we're doing is it's called empirical Bayes. So we're finding the posterior mode of all the parameters, including the hyperparameters, and then we're fitting an approximation to the kind of posterior around that mode. And so this isn't really considering the sort of interactions between different parameters. So typically, especially for hyperparameters, as you go into one area of the posterior for the hyperparameter, the covariates will change a lot. And we're not fully considering that in these models. You can do full Bayesian MCMC with this package. So you can use this package called TMB-stan. Then you can do all the steps that we just did. And then instead of fitting the model, you can do this make model object function. So if you make this model object, you can then use this TMB-stan function, which is doing full MCMC using the sampler that Stan uses. So it's a kind of best-in-class sampler. So if you want more details about this, you can look up TMB-stan or Stan. So this is full Bayesian inference, but it is slow. So for the Madagascar model we just looked at, as you saw, doing the empirical Bayes took about 5 minutes, 2 minutes. This full MCMC took us 90 hours to run, and that was after finding out how long we had to run it for. So it is very slow, again, mostly because there's all these pixels. So there could be interesting work to speed this up, but we haven't done it yet. But if you need full Bayesian MCMC, you can do this. Or what you might want to do is if you're fitting a load of models, you might fit one model in empirical Bayes and MCMC and compare them. When we compared our Madagascar model, the MCMC and the empirical Bayes were very similar. And in another paper, we did a similar thing. We compared the two. We did one MCMC and empirical Bayes and compared them, and they looked very similar. So especially if you've got a reasonable amount of data to learn the hyperparameters, the empirical Bayes will be fine. But if you need full MCMC, you can. And so there's just some references that is just here so that you can look them up because you've got the PDF. So that I went through that quite quickly this time. That's probably a good thing. Happy to answer any questions if anyone has them. Can you use results of empirical Bayes model as starting values? You could, but I don't think it will speed it up much. The slow bits of Stan is not finding the mode to. So there's two things. So the slow bit isn't finding the mode as a kind of a place to start from. The slow bit is learning the weights in the mass matrix, which helps it sample efficiently. So it wouldn't help for that bit. And they deliberately try and not having... The recommendation from the Stan team is you don't want your starting values to be too close together because you want multiple chains starting from different points to kind of convincingly show that your chains converge to the same distribution. So they recommend you don't use kind of similar starting values for all the chains. So it won't help for that, I'm afraid.
Thank you, Tim. That's really, really interesting. I just had a general kind of conceptual question. I kind of get the sense that a lot of the work that you've been doing with this and thinking about with this kind of method is for like fine scale mapping a lot of the time, so kind of predictive work. I'd love to hear your thoughts about the potential of these models for doing more kind of inferential work, like because that's kind of a lot of what I do with these sorts of spatial models. And I wonder whether you've got any thoughts about, their potential or their kind of limitations for doing more inference-based kind of work rather than solely predictive mapping.
Yeah, sure. So I think, so in terms of how the models are defined in things, I think they're totally fine for inferential work. And so really everything I have to say that makes inference difficult is the same for any other of these kind of similar spatial models with similar data sets. And I just think there is quite a lot of problems where quite a lot of the covariates you're using in kind of, you work on zoonoses and things or vector-borne diseases, a lot of these covariates are highly correlated, which makes it very hard to learn really true causal relationships. There's all the questions in causal inference where we don't know what to control for, and I think at least most of these sort of epi people I know don't really know the causal dependencies between their covariates, and so therefore it's difficult to do causal inference. So where's my picture of the covariates? Here's one. I guess temperature causes EVI, but maybe EVI causes temperature as well. At the in the under canopy, EVI definitely does cause temperature. What's the relationship between temperature, like standard deviation and stuff? And so to do like full causal inference, you kind of have to know the causal pathways between your covariates as well, which is very difficult. And I think we're always missing big important covariates. What we've found, we found that the spatial random field is always important. Therefore, we're almost certainly missing important covariates. But like the spatial random field is there to model those missing covariates, but it can only do it so well. Any kind of fine-grained variation in the covariates, it just can't model. And when we put like more anthropological variables in, they're often really important. So like accessibility is very important, but we know I really don't think we've got a good handle on the other sociological variables. So for so many of these things, like wealth is really important, and as far as I know, there just isn't good raster data sets for wealth. So all that stuff is just general. It's not specifically about these disaggregation regression models. So I think there is big issues with inference for this stuff, but it's not really relevant. It's not specific to these models.